Good afternoon, everyone. Thank you very much for joining our SpectrumX Radio Shop chat today. We're excited to have you here with us. Just a few things as we get started. So first of all, SpectrumX is the world's largest academic hub for innovating in the spectrum ecosystem in the US and around the world. The purpose of our Radio Shop chats is really to build the spectrum research community through education, collegial debate, brainstorming, and collaborations. And so today's chat is particularly significant because we're bringing together two major investments that the National Science Foundation has made here in the US. The Platforms for Advanced Wireless Research, or PAWR program, which we'll hear a lot about today, along with the Spectrum Innovation Initiative Center, which is now known as SpectrumX. So before I introduce the speaker, let's just run through a few ground rules. So these meetings are open to all participants in SpectrumX, faculty, students, collaborators, and friends. Your camera is preferable but not required. We do ask you to mute during the presentation. You're welcome to raise questions in the chat, and Tommaso, our speaker, has indicated that he's happy to take questions live during the presentation. And then finally, everything that you hear here today, you can carry with you, but we do ask you to obey the Chatham House rule, which is that you don't acknowledge or you don't attribute anything you learn here without permission. So we'll be going for about 45 minutes or so, and ideally have a little time for some Q&A and brainstorming at the end about how we can use these PAWR platforms to promote spectrum research. With that, let me go ahead and introduce our fantastic speaker, Dr. Tommaso Melodia, who is the William Lincoln Smith Professor in the Department of Electrical Engineering, Electrical and Computer Engineering at Northeastern. I'm sure many of you know that. He's founding director of the Institute for the Wireless Internet of Things, and he's also the director of research for the PAWR Project Office. He's an IEEE Fellow, NSF Career Awardee, and fantastic colleague. So we're very thankful again, Tommaso, that you've taken the time to help us come up to speed on how we can get more involved with the PAWR program. Take it away, sir.
Thank you, Nick. Thank you for the entire SpectrumX team for having me. Great pleasure. I think, it's a great opportunity to try and create additional liaisons to between these communities, and I'm glad to be here. So today I'm going to be wearing primarily my hat as a member of the PAWR Project Office, PAWR PPO. So what I'm not going to do is talk about my research or anything like that. And I'm going to try and give you a sense of what has been happening within the PAWR program, including things that we've been doing at Northeastern related to that to enhance the PAWR program with Colosseum, and we're going to be talking about that. Okay, so what is the PAWR program in general? PAWR stands for Platforms for Advanced Wireless Research, and it's a public-private partnership that has been funded, spearheaded by the National Science Foundation and a group of 35 leading companies. It's approximately a 100 million program where the National Science Foundation has made a significant investment matched by contributions from industry, primarily in terms of in-kind and engineering contributions. The goal is to create 4 city-scale testbeds for advanced wireless research to accelerate fundamental research, to accelerate applied research in wireless communications and networking technologies. What's quite unique about the PAWR program is that it's been conceived from the beginning to bring together researchers, industry, and communities. Researchers, obviously, to provide functionalities and capabilities that are not available in small labs that are normally stood up by individual research groups. In industry brings together, obviously, the market focus and perspective, and the idea is to get industry to work together with researchers to accelerate potentially new disruptive technologies and expose industry to the pool of resources as well as talent available in the academic community. And then the sort of the third leg of the PAWR program is the communities. The idea is to get local communities to build core wireless capabilities through partnerships with academia and with the industry at the national level and at the local level to provide advanced local services. PAWR, the way this has been organized is the National Science Foundation has stood up an entity called the PAWR Project Office. The PAWR Project Office manages the program. It's been funded by the National Science Foundation, and it's composed of US Ignite and Northeastern University. I think we have in the call also Mari Silby today, who is the program director for the program at US Ignite, and with whom we've been working very closely over the past few years in the PAWR program. This is the sort of the roster of industry players in the PAWR program. As you can see, lots of companies, traditional wireless space operators, manufacturers, but also companies in the networking space and other players. Now, PAWR started in 2017. As of today, PAWR has made 4 awards for platforms. And this platform, 3 of them have declared general availability. One of them has been awarded recently, and they're still working on their general availability. Some of the general principles that the program has been based on, right? So in general, we early on worked to decide on what were some of the criteria that PAWR platforms had to fulfill to be able to serve the community in the right way. And we wanted to, obviously we wanted PAWR platforms to serve a different set of stakeholders, right? They need to serve the general academic community, and so be able to provide functionalities that academics may need for basic research. They also need to provide advanced functionalities for industry, things that the industry may not have immediately available. And they need in general to be open and programmable as much as possible. So here's the list of the various criteria. Reproducibility for us was a very important criterion, right? We wanted to make sure that platforms would enable research by academic and non-academic groups that could be replicable and usable by other groups. Usability, and we from the beginning we tried to define usability on at various different levels, right? So platforms should have a number of hooks through which novice researchers can implement experiments and run applications on the platform, but they should also be more programmable at a deeper level to enable experimentation from expert users that are not just happy with running a network and seeing what they get out of it. So programmability has been an end-to-end programmability, fully programmable infrastructure with clearly defined interfaces, architectures, and APIs has been a very important goal from the beginning. Interoperability, provide interoperability between platforms and also between different technologies within platforms. Open access, so the platform should be available for the academic and industrial community at large. Diversity in terms of research areas of focus on the different testbeds, and sustainability. We wanted to select teams that had a strategy for providing sustainable support for the platform in years to come. Now, another important aspects of the platforms is that 3 of them, and we're going to talk about it, have been designated as, have received the designation as FCC Innovation Zone. What does it mean for a platform to be an FCC Innovation Zone? It means that there is a very specific geographical footprint associated with the platform and a set of frequencies that can be used for experimentation with a streamlined process where it's usually possible to obtain an experimental license in a matter of days or weeks and not months, as you would normally have with an experimental program license. Can you still hear me? Yes? Yeah. Okay, great. PAWR platforms that have been selected so far. There's 4 awards that have been made. The first one went to the PAWR Renew platform in Salt Lake City, Utah, which is focusing on a software-defined cellular network and massive MIMO capability. The second award went to the Cosmos platform in Manhattan, in West Harlem specifically, that is providing a suite of technologies with strong emphasis on millimeter wave and programmable optical backhauls. The AirPower platform is looking at really providing capabilities at the intersection between unmanned aerial vehicles and advanced wireless technologies in 5G and 6G. And the ERA platform, the most recent award, is focusing in Ames, Iowa, focusing primarily on rural broadband and ag-tech technologies. In addition to this, not directly funded through the PAWR program, but sort of initiatives that have been affiliated with the PAWR program, is Colosseum, the world's largest emulator of wireless system, which is now located at Northeastern University, has been inherited from DARPA, and the Open Air X Labs, which is an end-to-end open source 5G software lab. Okay, so going through some of the capabilities available through the platforms, and obviously we're going to stay at a high level, and if there is interest specifically on using one of the platforms, well, they are all available through their websites, but we're also happy to broker introductions with the PIs that are specifically managing the platforms and facilitate all discussions that might be of interest. So PAWR is, as I mentioned, in the Salt Lake City, Utah. It's primarily being supported by 2 different. Hold on one second. I mentioned that the kids might storm into my room. They didn't, but they stormed into my earbuds. So I'm hearing. Okay, so PAWR, the PAWR project, as I was saying, in Salt Lake City, and came from 2 different teams joining forces. A team at the University of Utah, led by Cobus van der Werf, and a team at Rice University. And PAWR is a platform for open wireless data-driven experimental research and renew reconfigurable ecosystem for next generation end-to-end wireless. The second one, primarily renew, focusing on massive MIMO capabilities. So PAWR is specifically a collaboration between the University of Utah, right? Utah Education Telehealth Network in Salt Lake City, deployed in the University of Utah campus and in downtown Salt Lake City. Includes software-defined base stations that are deployed on rooftops, significant access to compute, storage, and cloud resources that are deployed at the edge. So they are one optical link away from the radios and digital baseband processing on the radio, and a control framework for remote access and control. The research focuses on end-to-end programmable networks, spectrum management, and massive MIMO. Here's the footprint of the PAWR deployment. I wanted to mention, through the partnership with Renew, the access to programmable and observable software-defined massive MIMO platforms. That's quite unique. And that is something that is in many ways available today, if with some limitations for over-the-air transmissions. PAWR has 9 rooftop nodes today that are deployed based on soft SDRs. So each rooftop node has various SDRs, RF antennas to operate efficiently on band 7, and various pieces of equipment for monitoring and data capture of wireless signals. There's also a number of fixed endpoints that can be used to instantiate softwareized UEs. And there's more recently, PAWR has announced the availability of a number of mobile endpoints. So you have mobile edge computing as well as wireless software radio devices that are run on buses. And so they can provide mobile UEs with controlled mobility. There is also one massive MIMO base station that is, again, programmable base station. There is a controlled RF environment, which the PAWR folks call the Phantom Net, provides connectivity, edge computing, cloud access, significant cloud functionalities, and there is an upcoming denser deployment. This is just a little bit of to give you a sense of a map with rooftop base stations, fixed user endpoints, etc. What you have available through PAWR. And then the fully programmable massive MIMO base station, what you see here, it's based on daisy chaining of a number of software-defined nodes, and all connected with antennas. So you have the baseband processing for each individual flow on the base stations that it's separate. The hardware is provided by a company called Skylark, and Renew is providing an open source code base running on the Skylark hardware, and PAWR is integrating everything in the experimental framework that is provided by PAWR. Then I mentioned also the data center cloud functionalities. That's based on a cloud lab facility that University of Utah has been involved with for a long time. Significant amount of servers, cores, storage, etc. And availability of a lot of open source stacks like OpenStack, and availability of a number of profiles that are available to users to play with. So the PAWR is based on the concept of profiles. Profiles include software stacks combined with radio software and compute resources. So there's a number of template profiles that are made available to users to play with and experiment with, to build their experiments on. And obviously users also have the capability to create their profiles from scratch or by modifying some of the existing profiles. Some profiles are very easy to instantiate and play with. For students, there's profiles that just instantiate the GNU radio on a software radio. There's profiles that instantiate complete functional software stacks like SRS run on operating interface with a core enabling a functional network. And there's also other profiles that are more complex to use, like entire own-up instantiations, like what you see in the slide here. In general, what you see here on the left are some of the profiles available. There is SRS run, open air interface to generate both 4G and 5G softwareized and virtualized networks, GNU radio stacks, profiles based on OpenStack, entire end-to-end own-up profiles. There's an ORAN profile that includes a RAN intelligent controller that can be connected directly to an SRS RAN instantiation, so they can enable a lot of interesting research with XApps and control through the RIC at the edge, and various other research profiles that have been developed by the teams or some of the users of the network. It can provide a lot of capabilities in terms of radio frequency measurements, edge computing with real edge computing and real edge computing stacks that are one optical link away from the radio. Lots of work on disaggregated RAN, massive MIMO, mobility, and spectrum sharing. I also wanted to mention the spectrum monitoring capability that is available through PAWR. So there is a systematic data collection that runs every 6 hours at all the fixed endpoint nodes, and it basically takes measurements of the spectrum used between 0 and 6 gigahertz at specific instance of time. So there is a link to live RF monitoring data that the PAWR folks provide, and I'm glad to provide the link if anybody's of interest. And I thought this could be a capability of interest to SpectrumX in addition to all the others for sure. Now, getting to the second platform, Cosmos. Cosmos stands for Cloud Enhanced Open Software Defined Mobile Wireless Testbed for city-scale deployments. It's a award that was made to a team led by Rutgers University. Professor Rachel Lurie at Rutgers is the principal investigator of the program, and that includes also Columbia University and New York University in significant roles. In addition to a number of other partners also in the Cosmos Consortium, all of these consortia have included a significant number of partners from university, industry, academic communities, etc. Location is in West Harlem, New York City. The platform includes large and medium-sized software-defined base stations with fiber connections from the radio sites to local data centers, and opportunities for interaction with other smart communities and innovation initiatives. The research focus has been on a number of different things, but I'd like to highlight the millimeter wave radio communications and the presence of programmable optical backhauls for experimentation with, there is an intersection between the radio component, radio access network, cloud, edge computing functionalities. This is the footprint of Cosmos in West Harlem with large rooftop nodes, medium nodes that are at the street level, and small portable nodes. Some of the research domains enabled by Cosmos. Of course, you can find more information on the Cosmos website, and this applies for all of the platforms I'm going to mention. Being able to reconfigure optical paths for connection between the mobile cores and the radio access network. Edge cloud functionalities. There's also in Cosmos profiles to enable experimentation with management and orchestration frameworks like PAWR, processing in real time with data connected, obtained directly from radio nodes, for example, real video of a smart intersection. Lot of emphasis on full duplex wireless. There's full duplex capabilities both in a sandbox and on medium node experiments. There is capabilities for dynamic spectrum access work with and the trade-offs between use of different databases, different kinds of databases to enable experimentation. Third platform, the AirPower platform, as I mentioned, deployed in North Carolina, aerial experimentation and research platform for advanced wireless, consortium led by North Carolina State University. PI is Ismail Guvench, who is leading a team that includes support from the Wireless Research Center of North Carolina, Mississippi State University, RANSI at the University of North Carolina, Chapel Hill. The location is primarily in the town of Cary, in the Lake Wheeler Field Laboratory and in Centennial Campus in Raleigh. The resources include a combination of fixed software-defined radio nodes, unmanned aerial and ground vehicles that carry air power nodes. So you can think of aerial drones. They're a combination of aerial drones, some of them commercial, some developed internally within the team that carry software-defined radios so that are programmable, that can instantiate profiles defined by the air power team or by other users. The mobile nodes can be used as base stations, and be used to experiment with mobile base station nodes, or they can be used as UEs connecting to fixed base stations. So you can emulate a number of different rural and urban environments, create a number of remote access control, play with the remote access control framework, and with an emulation capability through which you can run and experiment in an emulated environment. And then once you're happy with your emulation capability, run it on the wireless nodes. The research focus is again the intersection between advanced wireless and mobility. It has the goal of accelerating the integration of unmanned aerial systems into the national airspace, and to advance the wireless features of US platforms, including flying base stations, hotspot wireless connectivity, etc. Again, it has, like the other two platforms that we mentioned, significant emphasis on software-defined networking, programmability, end-to-end programmability from the baseband processing up to higher layers of the protocol stack, applications, edge computing, and the like. This is showing a little bit of the footprint of the air power development. What you see here is the deployment in the Lake Wheeler area, just a little bit outside of the North Carolina state deployment. So very rural environment where it's easy to experiment with mobility and flying drones in environments that are rather unobstructed. Okay, I'm not going to go into all of the details of the current deployment, but Air Power already has a significant amount of devices that have been deployed, 3 fixed nodes that can be used to provide connectivity. They're based on software-defined nodes, etc. There is a deployment of various Facebook telegraph radios, millimeter wave, 60 gigahertz. They can provide functionalities primarily for channel sounding at those frequencies, and a number of other nodes that are under development and deployment now. Fun work, actually. I'm sure you can see from some of these pictures. The last platform that has been awarded, this one is not generally available yet, unlike the other 3 that I mentioned so far, is the ERA platform, led by a team from Iowa State University, with support from University of California, Irvine, Ohio State University, and International Computer Science Institute, agriculture and rural communities, and is an at-scale platform to enable experimentation with a number of use cases for rural broadband, agricultural technologies. In general, technology can serve rural communities, like the rural community in central Ohio where it's deployed, which will span a diameter of 60 kilometers. The idea is to make this a wireless living lab for smart and connected rural communities, and enable research and experimentation in this area with connectivity, broadband connectivity over large scales, as well as the ability to experiment with data collection platforms, agricultural IoT, and things like that. This is a little bit of the footprint of the ERA deployment, and a lot more will come in the next few months as far as AI is concerned. Now, a couple of other things that I wanted to mention maybe before opening the door for questions. I mentioned Colosseum. We consider Colosseum to be a PAWR affiliated platform, part of the suite of platforms in the PAWR program. Colosseum is the world's largest emulator of wireless system. It's something that was developed originally by DARPA to support the Spectrum Collaboration Challenge, which was trying to develop new collaborative AI-based techniques to support, to share spectrum, new blue sky approaches for spectrum sharing. After the Spectrum Collaboration Challenge ended, Colosseum was moved to Northeastern, to a group at Northeastern University, where it's being supported by a CCRI grant from the National Science Foundation that is supporting, basically opening Colosseum to the research community in general, as well as its expansion and creation of new functionalities that are useful for the community, as well as its integration with a suite of PAWR platforms. What is Colosseum at its essence? It's you can think of this as a data center. Originally, it had the 21 racks of radios, high performance computers, and CPUs. It's been since Colosseum joined Northeastern, it's been expanded to 25 racks of radio with the addition of new radios, as well as new GPUs and computational capabilities. So it's a data center, but it has a significant number of software-defined radios that are connected to the high-performance servers, so that you can instantiate virtualized protocol stacks that run on the radios. What's also unique is that the radios are all interconnected with one another through a fabric of FPGAs, so programmable hardware that constitutes the Colosseum massive channel emulator. So you can program the massive channel emulator to create virtual environments where the radios in the system can operate as if they were operating in environments where they really interact with one another in the physical space. So you can do experiments with spectrum sharing, creation of environments in smart cities, and you just need to basically model on the FPGAs the environment where you want them to operate. Colosseum is able to run in real time the 65,100 megahertz channels that constitute the system. So it's 256 radios that are interconnected in a mesh with 256 radios. And so you have a total of 65,000 channels that can be emulated in real time, generating a very significant amount of data with full mesh networking capability, creating the interference components between multiple transmissions that happen at the same time on the channel. So in a sense, in Colosseum, you have in the same instrument, the realism that you get in an emulator. So you have hardware in the loop with a real hardware effects from the filters, from the power amplifiers, etc. But you also have the scale that you normally get with network simulators, right? And the full stack and the flexibility that you get with cloud applications. Okay, so you get all of these three in a single instrument, and that's there's a number of very interesting things that you can do with Colosseum already today. Just a little bit on the architecture of Colosseum to give you a better sense. Colosseum is organized in 4 different quadrants. Each quadrant has 32 so-called standard radio nodes. A standard radio node is a combination of high-performance computing server and a software-defined radio. Okay, and then the radios in each quadrant are connected with the massive channel emulator, which is, as I said, a fabric of FPGAs that implement in real time the channels between the various radios in the system. Okay, and there's a traffic generator that can be connected with the various containers that implement a protocol stack on the radios, and there is a significant management infrastructure and a resource manager through which experimenters can access to a portal a set of resources through which they can define experiments and schedule the experiments, automatically schedule the experiments on the resources that are available in the system. Just to give you a little bit, getting a little bit more into the weeds of how this works, as I said, the standard radio nodes are a combination of a server connected with the USRP X310. The USRP X310 transmits a signal that goes at, so to speak, at radio frequency into the system. There is another USRP radio inside the massive channel emulator. You can think of this as a glorified analog to digital converter that will down convert the signal, bring it into digital domain, and then feed it to the channel emulator where the signal will be processed. You will apply the channel effects, the path loss that you need to characterize the system. It will sum the components from different transmissions that need to be received at a certain device, and then feed it back to the devices that need to receive that specific signal. And with that, we have there is a so-called scenario server that feeds in real time the radio frequency taps implementing the FIR filters that characterize the emulation of the various channels in the system. Okay, I'm going to skip some details, but I just wanted to mention that there is in Colosseum, there is a tool chain. Part of that we inherited from DARPA, part of that we created at Northeastern that enables modeling of specific environments, right? So there are some limitations as of today. So the size of the environments that you can model in Colosseum is 1 kilometer by 1 kilometer, and it's the frequencies that can be used in the system are between 0 and 6 gigahertz. But you can use, for example, ray tracing software to create the to model the propagation characteristics of specific environments that you are interested in. And we have a software pipeline through which we can take the input of a software like Wireless Insight, put it into, and then sort of compress the model that is generated by Wireless Insight into a channel model that can be executed directly on Colosseum. Happy to provide more details if anybody is interested in that capability. I wanted to just mention before I open the ground for questions that a number of the testbeds that I described in the PAWR program in Colosseum have been designed and deployed with similar philosophies, right? Software radios, and then servers that can, they can run virtualized containers that can implement various applications for data collection, for control, software stacks with applications, etc. So one thing that one can do is to, for example, conceive an experiment that can be a data collection experiment, or it can be an experiment for testing a specific technology or an algorithm in an emulated environment, for example, in Colosseum, then use the same container to validate in a real wireless environment. At Northeastern, we have an over-the-air testbed, indoor testbed that we call Arena, that is designed with the same environment. But many universities have labs based on software radios and servers that could take a container and run it to validate in a real wireless environment. And then you can test at scale on the platforms in the PAWR program. And there's a number of functionalities that have been developed in the PAWR program. So for example, we have containers that can be used to test with AI, ML-based control of various wireless technologies. And you can experiment with the same container, both in an emulated environment and over the air with the various platforms. Same for spectrum sharing algorithms, data collection over the air, etc. There's a significant software infrastructure for ORAN-based experimentation in future generation cellular systems that lends itself very well for algorithmic research on spectrum sharing and on advanced efficient use of the wireless spectrum. A lot of these software pipelines have been made available by the various platforms, by Colosseum. So I'm happy to provide more details if anybody's interested, but I wanted to just mention that there is a significant infrastructure that is available today that I invite you all to take a look at and to sort of take advantage of. And this is 45 minutes, Nick, right?
Yes, thank you, sir. And questions have started to come in. So I can either hand them off to the folks that are raising the question, or yeah, that's probably the best way to do it. So let's just go ahead then. Scott Palo.
Sure. Thanks, Nick. Hi, Tommaso. Thanks for a great overview of the PAWR platforms. Very informative. I was just, had a curiosity where, AirPaw is focused on, unmanned aerial systems, and then, ARA is focused to some extent on precision agriculture. Although I'm aware of, some reasonable amount of work that's been done on using unmanned aerial systems for precision soil moisture measurements. So passive radiometry, obviously, the scientific measurement. So I was curious, is there a plan or a thought to having the ability to integrate unmanned aerial systems into the ARA site, and how, or are they sort of separate, where AirPaws fundamentally unmanned systems and ARA maybe is less so?
Yeah, so this is a great question. So I'm sure that there's work that could be done on ERA with unmanned aerial systems in that context. And I believe they may have also looked at specific use cases with unmanned aerial systems. The way the PAWR program has been looking at this, and the way we've been trying to sort of direct the various platforms, is that AirPower has a lot of infrastructure that is specifically designed to facilitate experimentation with that. For example, they have, I mentioned an emulation platform that they're developing, where you can sort of test your experiment before you deploy it on drones, and then they have personnel specifically that will take your experiment and run it on drones for you, right? That's something that will not be available by design on ERA. They will do different things that are a little more focused on the specific verticals that they're looking at. That doesn't mean that you can't do a lot of different things on the various platforms. It's just that you'll find more specialized infrastructure on the various platforms and expertise to support some of those use cases.
If I can just add something to that too, Tommaso, if you don't mind. This is Mari Silvi, Program Director for the PAWR Platforms, the project office. The other thing I would add to that, Tommaso's right. The infrastructure is really set up there for the drone flights at AirPaw. However, for example, there are agricultural fields near to the NC State sites as well. There are agriculture fields that AirPaw owns. So we have been talking, for example, to one of our partner companies about potentially doing a proof of concept with UAVs at one of those fields to do, essentially some kind of video monitoring and then processing of that information in those fields. So that is, it kind of goes both ways. There is the potential, to potentially bring, UAVs or other airborne or a helikite, for example, to Aero, which has been talked about as a possibility. But there's also ways to deploy those drones, potentially depending on the use case at AirPaw as well.
Great, thanks for the clarification.
Next up, Jeremy Thorley. You're still there?
Hey, no, thanks, guys. So I guess for me, I'm just curious, could you go over sort of one of the experiments you might use PAWR for? Or is there anything specific you're looking to test with it, or just anything like that?
That's a very broad question, and I'll take a shot at it. We are trying to enable capabilities that will be useful for the research community to be able to do research, right? So I can start maybe from examples of research that I am interested in and that can be enabled by some of the PAWR platforms. There's been a lot of interest in the last couple of years on providing optimized AI-based end-to-end control and orchestration functionalities on open, programmable, and virtualized wireless systems, right? So using basically AI to control on a fine grain cellular systems that are softwareized. This is something that today already PAWR offers unique capabilities to test in this space. I would say that in Colosseum, you have the capabilities to experiment at scale with softwareized wireless network. We can instantiate networks with 60, 70 nodes in an emulated environment and test at scale with AI-based algorithms on running intelligent controllers. You can take those experiments and run them on PAWR, both in their emulation environment and over the air. Mari will probably be more precise than I can be on what are the specific frequencies that can be used for that. But in general, you can do that. And same thing with Cosmos. There is a significant amount of infrastructure to test with control of softwareized wireless systems. There is a number of experiments that are related with data collection to develop AI agents and AI inference modules that can, I think, already be enabled uniquely by some of the PAWR platforms. You can collect waveforms and frankly, full protocol stack information as transmitted over the air with a number of the PAWR platforms, and do the same, basically conceive data collection experiments that can be repeated in a number of different heterogeneous platforms to provide data that can help you generalize your models. And this is available today. There's capabilities that can be enabled in terms of spectrum sharing. There is a team from the Spectrum Collaboration Challenge that has continued the work that they were doing in the Spectrum Collaboration Challenge, both in Colosseum and in PAWR, to enable spectrum sharing between multiple OFDM systems sharing the same frequency bands in a cooperative way. And they're doing this work in Colosseum and over the air in PAWR. This is just a bunch of experiments that are very close to research that I am personally interested in, but there's a lot more.
Yeah, I would put a point of emphasis on two things that Tommaso said. One being the data collection piece. The capabilities and the infrastructure is here to do this data collection. What's not necessarily in place is the framework to decide how the data should be collected and categorized and shared and all of these things. And that is the kind of, the kind of work that I can imagine coming out of a hub like Spectrum X, which is, somebody or a group of somebody's deciding, here is the type of information it would be good to collect. Here's the type of data it would be good to collect. What would happen if we collected it in this way, if we gave it this type of metadata and fields so that it could be, again, reproduced in different environments and compared and stored and analyzed. That's kind of one of the major opportunities that I think is out here with the PAWR platforms. The other thing that Tommaso mentioned, and I'm just going to reiterate it here because it gets to one of the questions in the chat too, which is the ongoing work that's being done out of one of the finalist teams from the Spectrum Collaboration Challenge. So they are actually coming to the end of the funding, the first round of funding that they had, that was from DoD, combination of DoD and NSF, bringing this team to Coliseum and to PAWR to run what's essentially an ML or an AI engine, to try to get sort of more fine-grained allocation and dynamic allocation of spectrum. And they have been demonstrating that, again, both at Coliseum and then over the air, with the idea that the next phase of that will be to do more security-focused development, to be able to show how, particularly for the DoD, some of these things can be considered and in an environment that is secure enough for the type of operations that DoD would consider. I mentioned that also because, to me, that is a fantastic example of the collaboration at the federal level that often needs to take place for sort of successful furthering of the research here. This was, DoD and NSF saying, here's a problem we want to solve. Here's an investment that's already been made. Let's use those resources that we've invested in, build further on them, use them, develop solutions to the specific problem we've defined, and then see what we can do next.
Awesome. Thanks, guys.
Josh Weaver, did you want to pick up on that topic, or did Mary and Tommaso address your question?
They mostly addressed it, I think. It sounds like that they're at least thinking about that security aspect of it, and fully concur with the whole of government approach to this problem. I know that the Wireless Spectrum Research and Development Group they're having an extended meeting next month. It's government only, but the whole topic of the meeting is spectrum sharing. So I think it's a hot topic right now, and we've got a lot of ground that have covered it and that we will cover in the future. So I'm happy to see people talking about it. The one question I did have in response to that previous answer was that phase 2 work where they're looking at the security. Is that currently funded, or that's a proposed effort?
I won't say it's a guaranteed funding, because it relies on various government things to happen, but it is virtually so, and expect to be able to talk about that in the near future.
It's one of those things that you expect to be funded.
What was that, Tommaso?
It's one of those things that you expect to be funded.
Yeah, very, very, yes, very, very much expect.
Okay,
we'll see what
Charla.
happens on Friday when the current continuing resolution expires.
Ding, 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 ding.
Charla Rath, did you want to jump in?
Sure. Thank you very much. This was really interesting to hear where things stand with the various test beds. I was actually engaged early on in this when I was with Verizon, and clearly one of the things that NSF was trying to accomplish here was to set a very, sort of a tight private public partnership with both the public sector and the private sector contributing, and again, beyond the university and the research community. And I'm sort of curious, this is stepping back a little bit from all the technical information that you've been giving. I'm curious how that has been going on both the vendor and the operator side, because certainly my experience was those two communities actually approach research in a very different way. And it was very obvious as we were leading up to the RFP phase. And so it's quite interesting to me to watch it at that stage to see how, the AT&Ts, Verizon's, T-Mobile's, but also Nokia's and others would participate in this. So I'm just curious how that's been and how does that work at this point in stage? I know that PAWR has a number of corporate sponsors and, just sort of curious how that's working.
Mari,
Also,
do you want to take
I
this
was going to say,
directly?
do you want me to take that one?
Yeah,
The
go ahead.
non-technical
I had a
question here.
feeling you might. I had
Yeah.
a feeling you might.
So I think the track record is mixed. When we started out with the industry consortium and all of our partners, the primary early focus was what could we get these partners to contribute to the platforms? So what major equipment and engineering support and software licenses could we beg, borrow, and steal from them to add to our resource bucket for deployments on these platforms? It's different now that we are into, sort of the first year or two of like full operations for a couple of these platforms. Specifically the PAWR and Cosmos one. So I can give a couple of examples where, we've started to move the needle a little bit more into the research direction. In terms of with our partner companies. One example of this is through activities with the Open RAN Alliance. Both PAWR and Cosmos were part of the global plug fest that took place at the very end of last year. And one of the pieces that came out of it was AT&T ran a proof of concept to show how their sort of overarching management and orchestration system could be used in an emergency situation to create a slice of spectrum across different sub-management and orchestration systems. So in theory, slicing off a piece of spectrum across multiple networks, that's what it would be like in the real world, multiple carriers, for example, and showing how that could be, again, sort of sliced off and managed securely and independently solely for first responder communications, as an example. So both Cosmos and PAWR participated as sort of host spaces for that exercise. So that's one example. We have another partner, a vendor partner, who's actually been very engaged and is I don't know how much of it's public yet, so I probably can't say too much about it, but is looking to do some proof of concept demos on both with the UAVs and then also at the rural platform when that launches later in the year. I had another example of some of the company research. Oh, I was going to say the last thing I would mention is that, and this was very interesting and heartening to me. So one of the things that we had pitched to the carriers in particular was that we know they have their own labs and testing grounds and production networks, obviously. The whole part of what we're trying to do in the telecom space is to open up the system to allow in more entrepreneurs and more innovators. And the idea that carriers are unlikely to let sort of newcomers onto their production or potentially even testing systems. So we have pitched to the carriers, that's okay if there's somebody whose technology you are interested in, but they need to develop it further before they can potentially bring it into your labs. You should send them to us. Carriers, you have contributed to these platforms. We can now turn around and say one of the benefits that you get is if you want to see a startup company test their technology somewhere in a real life environment, they can come to our platforms and do that. And because you've contributed, we can subsidize some of that. And we actually had that happen. Somebody just reached out in the last couple of weeks who is interested in both Coliseum and PAWR specifically, and was referred by Verizon. So that's something we're exploring at this point and really hoping to see more of in the future.
Great, thank you.
Thank you.
Okay, in the interest of time, I'm gonna call it there. I know that Mike Honig had some interesting questions about MIMO parameters, but maybe we can follow up with that one offline. I'm sure there are many.
We're happy to connect them to the experts on the ground on that, but yeah. But it's
so let me just
32 antennas in the one that is already deployed, and it's CBRS, right, Mari?
Sorry, I'd actually have to go
Massimo
back and check on
109 on powder.
which spectrum it's using. I think you're right, but I'd have to check.
Yeah, I also have to check. But yeah.
So let me just wrap us up. First of all, let's all thank Tommaso and Mary and also Yvonne from the PAWR program for joining us for today. It's really great to bring you all together. The purpose of our spectrum. What's that?
Where is Ivan? I didn't see him.
Yeah, well,
Okay.
I'm here.
he's still there. Very
I
good.
am.
The purpose of these Spectrum X Radio Shop chats is really to build community. And we've done a great job here today talking about these different resources that NSF has already invested in. We've got a couple ideas already for potentially shaping some data collection and planning for archiving and use of the data. One other food for thought is that Spectrum X has a significant education and workforce development mission. And I think that maybe brainstorming how we bake some, use of these platforms into the curriculum that we develop and push out to students and researchers might be a pretty good opportunity for us to pursue. So I think there's lots of opportunity for following up, and I look forward to doing that with you all. With that, I think we should close down the session for the day and look ahead. We also are very open to taking suggestions for future Radio Shop chats. And with that, I'll close the session. Thank you all very much.